Okay, last time we looked at the time dependence of an operator, and we had this relation that if I have two operators and corresponding two measurements, so if I look at the uncertainties in the measurements, delta A and delta B, I found out that this was greater than or equal to 1/2 the magnitude of expectation value for A and B. Okay. And also, okay, so this was a generalized uncertainty relation. But we also looked at the change in the expectation value of an operator A, and that was equal to 1/pi h bar, okay, expectation value for commutator of A with H. Okay, so these are things that we looked at last time. Remember that these expectation values are always with respect to some size. Okay, so these delta A's and delta B's are all with respect to a certain wave function. Now we can combine these two expressions to find a new type of uncertainty relation, which is called the time energy uncertainty relation. Now this is a little bit different from the other cases because we have the time in it. So when we say time and energy, energy of course is associated with an operator H, but time is not an operator in quantum mechanics. So we do not have, we cannot treat it as an operator, but still there is some means by which we can associate an uncertainty relation. Now there is one obvious one. Okay, so in our discussion of the wave nature, we have the wave nature of the object in position space, okay, given by this k, which is 2 pi or lambda. But we also have the frequency and time relationship, where this frequency now is related to energy, right? So this k, remember, is related to momentum over h bar, and this omega is related to energy over h bar. Okay, so if you have an uncertain relation between momentum and position, okay, you expect same type of uncertainty just because of the wave nature of things, right? So if someone, for example, tells you, okay, what is the wavelength of something like this, okay, you could be tempted to say, well, the wavelength is this, but not really, okay? This would be a wavelength if the wave extended from -infinity to +infinity. To understand what the wave structure of this is, you have to extend this in terms of, okay, all types of waves, it's all types of wavelengths, okay, add them up. Indeed, you are going to get the largest contribution from a wave which has that wavelength, okay? But there will be many other wavelengths, in fact, infinite number of wavelengths, okay, which then tells you that there is some uncertainty. So there is some uncertainty in x, which is delta x, okay, which then relates to the delta p, okay, which is the uncertainty in the wavelength. Now, just from the mathematics of things, whatever is happening here must be happening here also, right? If someone tells you what the frequency of something is by giving you a sample only for a certain interval of time, okay, there's some uncertainty in determining that frequency. Okay, because if you had a sine wave going from minus infinity to plus infinity, then you would definitely know what the frequency is if it's just a sine wave. But if it says it has some finite content, then there's some delta t associated with it, and there should be a similar amount of delta omega uncertainty in the measurement. Okay, just because you cannot construct the frequency out of these things. Okay, so just looking at this equation, what we'll do is we'll try to understand how we can put in a delta t into this equation. Okay, so what I will do is I'll try to arrange an experiment. So here's my psi. Okay, this is my state, which is changing as a function of time. Okay, otherwise I don't get, obviously, okay, there's nothing that doesn't change in time in quantum mechanics. It changes according to the Schrödinger equation. That's why we get these time dependencies. Okay, so this psi is coming in, and I'll try to measure, just like what we did here. Remember our experiment, we tried to measure A or B. Now this time, I have the option of measuring, okay, putting this particle into this experimental apparatus, which makes an A measurement, or possibly, okay, so I don't know which, I cannot make both of them, or I'll put the particle into this H measurement, okay, and try to find out what its energy is. Okay, so both experiments have possible outcomes. Okay, so there is going to be some mean for both of them. Okay, so here's going to be the average value of A, but it's changing in general. Okay, so it's slowly changing. And the average value of H now, that is something that is not changing, because we know that H value itself, if I know the Hamiltonian, the expectation value of energy does not change. Okay? But now I want to make these measurements, so that I am hoping that this psi is not changing these things that much, so that I can make an accurate measurement. Okay? So I'll try to make an accurate measurement as this wave function passes through these objects, either one or the other. Okay? Now, let me just put this into my equation. Okay, so I'll take this equation, take the magnitude of both sides, so that the A, the T, okay, magnitude is going to be equal to 1 over h bar, magnitude of, okay, commutator of A with H. But that thing, okay, so if you now look at this first equation, is related to the uncertainties in A and H. Okay, so if you help me with my algebra, there's 1 over h bar, but I also get, okay, so 2, this is less than or equal to, right? 2 over h bar, right? Delta A delta H. Right? So H bar factor is here, and I have just written this equation, okay, so that it looks that way. Okay, so let's now look at this equation. There's some change in the expectation value of A, but there's also some uncertainty in the measurement of A. Okay, so I'm trying to make as accurate a measurement as I can, but at some point, okay, this change in A, if it becomes more than uncertainty in A, that's not a good measurement, right? Okay, so this A, although it's changing, I want to limit, okay, my wave function, whatever measurement that I'm making, to a case where this dA is approximately of the order of delta A. Okay, so what does that mean? If that is not occurring, if this dA is much larger than delta A, etc., then it's not a really very accurate measurement anyway. So I want to keep my measurement as accurate as possible. Okay, so I want this, then this dA dt to be of the order of delta A, okay, some delta t. Okay, where this dA is of the order of delta t. Okay, so if I write this equation again, I'm going to get delta A over delta t is less than or equal to, okay, 2 over h bar A delta A, and in place of delta H, let me put delta E as general certainty energy, delta E. So I get delta E times delta T, okay, greater than or equal to h bar over 2. Okay, so you see we have gone through a somewhat roundabout way of obtaining this, but what we have obtained at the end is what you would expect from the general discussion of wave nature anyway, right? So we have this e to the I kx minus omega t, and this just says that if I have a delta p delta x uncertainty of the order of h bar over 2, then I should also get a delta e delta t uncertainty of the order of h bar over 2. So this is how that sneaks in, okay, into our analysis here. So what does this mean? Okay, actually you can, the effective observation of this is much more really straightforward than the theory that produces it. If you are limited in your time in measuring a phenomenon, okay, when you are making an energy measurement, then that time constraint results in error in the energy measurement. Okay, so suppose, for example, we want to make a very accurate quantum clock. Okay, so we want to make a very accurate clock so that we put it in these GPS satellites, which are supposed to keep extremely accurate time. And one way of doing that is you take certain atoms with, okay, 2 level states, and then you look at the transitions from one state to another. Okay, it's a nice quantum mechanical system, and these things, as you make transitions, these things just, you offer radiation, and then you just take this frequency, divide it by a certain amount, which makes your clock signal so that your clock runs extremely accurately. So you want very accurate clocks that are flying around in these satellites, and they are based on these atomic clocks, which correspond to transitions of the electron from one state to the other. Okay, but now, what do these things look like? Okay, so if I want to make an energy measurement, okay, so there's going to be a transition from a certain energy level, okay, there is supposed to be one energy level here, and there's another energy level there, okay, and you could say, well, okay, these are two well-defined objects, so I have a certain well-defined frequency between them. But when I am making this energy measurement, there are certain effects from the environment that come in. Okay, so I want to look at the transition, okay, energy from this state to that state, but the atom, okay, bumps into something else and is disturbed. So when you have this collision, it no longer has the same Hamiltonian. It's, okay, messed up a little bit. So I have a certain uncertainty in the energy that I am measuring. So this energy level is not something, okay, infinitely thin like this, but it has a certain amount of width. Okay, so it has a certain amount of width which corresponds to some energy uncertainty. Okay, so this is my delta E. Okay, and makes a transition. Obviously, you can make similar arguments for this level also. Okay, that gives you a certain energy uncertainty, which is related, obviously, to since delta E is equal to delta H bar omega. Okay, that's then gives you some uncertainty in your H bar is not changing. So in the frequency that you are trying to measure here. Now the point is, this event here is going to be wider if the state has a lower lifetime. Okay, so large delta E, okay, is associated with shorter, okay, lifetime. So here I'm looking at this atom, okay, trying to measure this frequency, but this thing now bumps into another atom. That's why you need low density gases if you want a very accurate measurement. If the density is high, of course, there will be more interaction between these things, which will make things more messed up, right? If you have very many interactions, then even your Hamiltonian starts to become questionable. So we want these things flying around for long periods of time, during which time you can make these measurements. So if you want more accurate flux, maybe you should go to lower temperatures or something, okay? So that things do not interact that much. Okay, so shorter lifetime means this is going to be wider. But if you are treating your system well, okay, so if you have made a nice high technology atomic clock, then you are going to get an extremely thin, okay, line here for energy. Okay, so this is going to correspond to small delta E, okay, which will correspond to longer lifetime. Okay, so longer lifetime means, of course, obviously, large delta T. So if you have large delta T, lifetime for the system, you are going to get a smaller delta E, okay, which will correspond to smaller variation in omega, okay, which will, again, same thing as a large delta T. Okay, so this is actually quite standard throughout quantum mechanics. If you have energy states which are wider, that means they are interacting with something. Okay, so sometimes in the seminars, okay, someone will give you a picture of the energy states in a system, and you are going to get a curve which looks like this, okay, some of them thin, some of them wide, etc. And the person giving the seminar will say, okay, here I have an energy state, there I have an energy state, there I have an energy state. But quite obviously, this energy state is somehow not being influenced by the environment. Okay, whatever the effect is, okay, it's not being influenced by the environment so much. Whereas these things, perhaps they are coupling to the vibrations of the atoms inside the, okay, solid, or it may be some other effect, okay, associated with, again, the environment of the system, and those things give you larger delta E's. Okay, so the delta E's, okay, corresponding to these things have various widths. So this is a nice, sharp, okay, energy state, which is not interacting with many other things, isolated, whereas these things are, okay? So, okay, at the end of the talk, you can look smart and ask a question, why do you think this is so sharp? It's not interacting with anything, and the seminar speaker will try to give you an explanation for 10 minutes, etc. Okay, this always works, so keep that in mind, yes.
Professor, how can we approximate the expectation of A equals to variance of A?
Okay, so this is you see, at the end of this discussion, we do not have even A in the problem, okay? So it's some sort of ancillary operator that we introduce into the problem just to make sure that things that are changing are not changing that much. Okay, so we have this measurement, possible measurement of A and B, which I had over here. Okay, so you see at the end we do not even have A there, but what we want to do is we want to make sure that we are making a relatively accurate measurement so that these things are as small as possible, okay, both delta E and delta T. So what we are doing is that this change of this average value, which depends on what the psi is, and it's changing as a function of time, okay? So I have a certain average value here, and also a certain uncertainty, which is the delta A. So if my measurement is outside this range, then obviously I'm not making a reasonable measurement, right? It's not, if the average is if the standard deviation, if the fluctuation is over here, and I'm getting a change in this delta A, which goes way off here, then I might not as well trust that measurement. So that is the largest delta A that I can have. Okay, so that's the logic behind setting delta A equal to this dA. So it's the amount of change in this average value. I set it equal to the amount that's, okay, so that's the limit of my measurement, that my average value has changed approximately by the fluctuation, okay? Fluctuation. Yes.
In the Cemal version of the A operator that we chose arbitrarily, why can't we put H itself there?
And the other way to get zero. That will give you
but it says
an unreasonable.
It says the Hamiltonian never changes, or energy never changes in any system. If we do.
No, we are not going to get a useful relation out of that, right?
No, that's not for that. I'm asking why can't we put? Because
You
it
can
gives a
put anything you like.
meaningless result.
Yes, you can put anything you like, but depending, of course, the result that you get, you are going to get zeros all over. Okay, with H, that's the average value of H is not going to change, but that's something you know because it commutes with itself, etc. Okay, so it's not going to be useful. Yes.
Shorter lifetime, does it mean increased frequency?
No, shorter lifetime means your system has other effects from the outside, okay? Shorter lifetime means normally, if I have an atom which is just sitting here, okay, and there's nothing acting on it, it will have an extremely long lifetime, okay? So in principle, according to the amount of quantum mechanics that we have learned, okay, the lifetime of that state will be infinite because the energy difference will be definite, delta E will be zero, infinite lifetime, okay? But there are other environmental factors, okay? If nothing, these things called vacuum fluctuations, the harmonic oscillator contents from electromagnetic radiation, the ground state of that results in spontaneous emission and such things. So even under the best conditions, you have some uncertainty here which results in this emission, okay, which triggers that. Now, the lifetime of that depends on the amount of external effects, things that you have not included in your Hamiltonian, okay? Things that you have not put in there, but those things that disrupt your measurements, okay? So hitting one atom with another, a collision, disrupts this, okay? So you have a measurement, you have a delta T, which is less than the collision time for these atoms. If they collide less, then you have a better measurement of delta E. And if there's a shorter lifetime, because of various effects, okay, you may have some, if this is inside a solid, then you have all kinds of things, okay, thermal motion of other atoms, etc., which disrupt these energy states, which you will not usually put into the simpler theory, okay, and therefore you get larger delta E's because of smaller delta T's.
So it has nothing to do with this omega.
Which omega?
The one related with the delta E.
Well, okay, this delta E is also associated with delta omega, right? This delta E is, if I want to right, internal omega, it's h4 times delta omega.
So what is delta T in this case? It's the time that clock measures or the time between measurements?
Okay, delta T is the length of the system so that it stays stable according, which obeys your model Hamiltonian for that period of time, okay? So if your system obeys your model Hamiltonian for an infinite amount of time, okay, then the energy measurement will be very precise. Okay? Yes.
So for the sake of comment, can we interpret dA divided by dt as we evaluate dA as variables, right? Some kind of variable. So it can be interpreted as the change in the expectation during the some interval.
Yes, okay.
So that's it, for the sake of the intuitivity, can we interpret?
Yes, okay, so you can sort of say that, in fact, this is that equation, right? It's how much this is changing, okay, as a functional time, how the average value of that is changing as a functional time. Okay, so you have calculated such things already, and you, for example, calculated things like what is the average position of x, for example, in the harmonic oscillator as a function of time. This is changing because the wave function is changing. Okay, so if the wave function is changing all the time, then of course you are going to get a change in this expectation value. If it's changing all over the place, then of course it's not a good measurement. So what we are saying is that suppose this change is small, of the order of delta A that you have for this system, and let's see what happens. Okay. Yes.
Can we say in the long run, everything in the universe will be stationary energy states, because if delta E is equal to 0, delta T is infinite, and other values are always fluctuating.
Okay, but these things are somewhat hypothetical, okay, so the questions about the state of the universe and such things now, if you can write the whole Hamiltonian for the universe, all particles, etc., then of course everything should be conserved, okay, but that is not of course a practical approach, okay. We tend to solve problems piece by piece, okay? But if you look at the whole universe, with all the particles, everything in it, okay, just one H, then of course you get H psi equals E psi.
Let's take isolated systems, and can't we also say that for that, like a bunch of cluster of atoms in a vacuum, and can we say it will eventually end up in a stationary energy state?
Not really, okay, so you have a certain H, okay, so if you take some system, you have a certain H, right? And you have these states which are UN equal to En UN, okay? Now, if the system is in one of these states, and if you have no other interactions, nothing disturbing the system, okay, the system will stay in that particular nth stationary state for all time, okay? But normally, you could expect that the state of the system is some linear combination of all these states, in which case there's no reason why it should go back to only one of them.
Yes, but all states are fluctuating except stationary ones. So won't they end up in stationary at some time? No?
No reason why, okay, you should, this thing should collapse. Okay, if there are external effects, then of course you put in those external effects, but then you are talking about statistical physics, right? Certain contact. Okay, other comments? This is not actually a very clean-cut, okay, argument for the time, energy time uncertainty relation. It is something that you expect to get just because we said, okay, it is expected because of the wave nature of things. But okay, there are various other ways of getting at the same point, and it is the only safest thing, only safest conclusion that you can actually get from this is the discussion that I gave you here. States with longer lifetimes will have smaller delta E's. States with shorter wavelengths, shorter lifetimes will have larger uncertainty in their energies. Okay, it's a fundamental uncertainty in the energy, just because you have this finite effect. And just remember the example of this time measurement. Okay, if you want to make a clock out of very simple systems like this, two-level systems, if they are isolated and alone, you can get very accurate results out of that, okay, transitions from one state to another. But if the amount of time that you have between measurements, delta T, okay, that's limiting your energy measurement is short, then that corresponds to, okay, larger uncertainties. Okay, so that's the result that you want to take home from that. Okay. Questions? Okay. Yes.
I think there's another less heuristic way of deriving this as well. just can't we use the normal uncertainty relation and then with T and H, but then use H equals I times delta over I times H bar times delta over delta T from the Schrödinger's equation to get the same thing as well.
Well, okay. But now, just in terms of algebra, okay, so you have this deep psi dt is equal to IH bar H psi. And what we are suggesting is that you put this into delta E and put that into delta T, etc., and play around with those things. Okay, you see the arguments leading to such things are always dangerous because you have, obviously you are going to get something like this just because of dimensional analysis, right? You have momentum times distance as the units of h bar, energy times time has units of h bar. So in many equations that you write down, you are going to get that structure, okay? H bar time energy, H bar time energy, and it appears all over the place. But attaching some amount of explanation to it, then of course becomes sometimes more difficult. Okay, so sometimes just dimensional analysis gives you the same equation. Okay, let's see how much time we have. Oh, 10 minutes. Okay, what I want to do in the remaining 10 minutes is, because I have assigned you this homework problem, I just want to open a parenthesis here and perhaps one more. Talk about the relationship between the Hilbert space formalism and the linear algebra approach that you must have seen earlier. Okay, so let me just say I have a connection with linear algebra. Okay, all the stuff that we are doing. Now, remember that I told you that this A operator can be put into identity states ij and circle ui uj. Okay, A ui uj, so these are the identity operators. And this thing here is our aij. Okay, so aij, suppose I have a two-level system, is going to be something which looks like A11, A12, A21, A22. Okay? So the question is, for example, if I want to okay, find so this is A. If I have given you this, okay, what is E to the A? Okay. Now we know that this is E to the A can be written as a series, okay, from the definition of exponential, something like that. But how would I go about calculating it? Okay, so what I do is I look at the eigenvectors of this object. So if I have A times psi I equals lambda I psi I. Okay, I'm going to get two eigenvalues and two eigenvectors. Now, if I look at the Hermitian adjoint of this, what do I get? I get psi I dagger complex conjugate, okay, a dagger with lambda I complex conjugate, psi I dagger complex conjugate. Okay, so this is the Hermitian adjoint of psi, okay, and A is the dagger is the Hermitian adjoint of A. But if I know that A is Hermitian, then this is equal to A again, and I know that it's Hermitian, eigenvalues are going to be real. And if I just call this thing a phi I, okay, so this is a column vector, this is a row vector, right? A is equal to lambda I phi I. So I get the same eigenvalue equation, except that now I have these things on the left. So this is the ket vector that we have been working with, and this is the bra vector. Okay? Bra and the ket. Okay. So if I now look at certain things which are involved with this, let me define a capital psi matrix, which is made up of, say, psi1 and psi2 vectors like this. Okay, so the 2 by 2 matrix, 2 eigenvectors, I put them in like this. What happens when I operate on psi with A? Well, psi times, okay, A times psi1 will be lambda 1 times psi1, and so on. So this is going to be lambda 1 psi1, lambda 2 psi2. So I have that. Now suppose what happens if I take phi on the left-hand side, a psi like this. Well, it's going to be phi 1, phi 2, right? Lambda 1, psi 1, lambda 2, psi 2. Now, this is a left eigenvector, this is a right eigenvector. We have this condition that phi I psi j is going to be delta ij, because these things are orthonormal. So what we are doing here is something like ui j inner product, right? Delta ij. So I'm going to get lambda 1, 0, 0, lambda 2. Okay, so what did I get? This is my, okay, a I, a j, right? If these are the eigenvectors of this, then I'm going to get lambda I, delta ij, right? We discussed that any operator will be diagonal in its own representation. So, if I want e to the a, what I can do is I can put identities, psi, phi, psi, phi, left and right. Okay, so I'll get psi, phi, identity, plus a, plus 1 over 2, a squared, plus 1 over 3 factorial, a cubed, etc. Psi, phi. So you see I already have a phi, a psi here, but let's just expand this. Psi, phi, psi, plus phi, a psi, plus 1 half phi, a, another identity, psi, phi, a psi. So I hope you can see what's going on here. I'm generating these diagonal matrices. Phi, right? So this is identity. This is psi h psi, which I already have here. Lambda 1, 0, 0, lambda 2, plus 1 over 2 factorial, square of the same matrix, which is lambda 1 squared, 0, 0, lambda 2 squared, plus dot, dot, dot. Okay, phi is still there, and psi is still there. So this is going to be psi, right, e to the lambda 1, 0, 0, e to the lambda 2, phi. Okay? So, since you know eigenvalues and eigenvectors, you have determined what this is. So this object here, which you can see this matrix in the center, is just ai e to the aj. Right? Remember this thing we said was going to be what? E to the lambda j delta ij. Okay, so you see this notation is so much faster and everything, but if you have to work with the matrix itself, with numbers, etc., then you may prefer to use your old linear analysis methodology. I hope you remember all of this, right? You did not learn linear algebra for the sport of it. You did it all over the place, right? So you should be very easily able to find the eigenvalues and eigenvectors of a 2x2 matrix and such things, because those things will come up. But then again, the first time taking this course is in your homework minutes. Okay,